So actually, Ram's talk had someone yelling at the clouds, and actually I'm that guy. I'm the guy who yells at the clouds because I started out my career as a control and geometry and dynamics person, and then this tsunami of learning stuff that everyone was excited about was very uncomfortable. And now, Frank mischaracterized my talk because actually I am going to show you robots that are locked in a room and that are supposed to learn on their own. And that's a lot about like what I want you to take away from this talk is what should we mean by the word or phrase robot learning? I think we do mean a lot of what we currently do. Do I think we do mean that we're going to use internet scale data to get robots to do interesting things? But I also think we mean, or should mean, other stuff. Because actually, internet scale data is a lot of data, but compared to the world, it's not very much data at all. And robots are going to have to operate out in the world. So I'm going to talk about why I think that's true. But first, just why isolation? When and why are robots isolated from each other? They might not have communication. That's one reason for isolation. But they also might have things like irreducible novelty. They're going to be in an environment where there's just something that's so fundamentally new that they cannot expect to simulate it or represent it before they encounter it. I am really interested in some of the examples I'm going to talk about are non-anthropomorphic sensors that can't practically be labeled. Or even if we do have anthropomorphic sensors, we don't have a mechanism for labeling the data. Then there might be sort of things that come down to manufacturing, so sustainment and serviceability. Like we might need to redesign robots so that now their physical properties make those things easier, but they're substantially less easy to simulate. And then decision-making in new settings that don't have any priors for some reason. I think all of this stuff is real stuff that robots are going to have to face at some point. And that really the only lever that we have from my perspective is that they have actuation. Actuation can dramatically improve data quality. If you have something, like right now people worry about out of distribution. I like doing experiments where everything is out of distribution. I'm going to show you examples of what that looks like. But good data is often scarce. Robots have to go out and get it. If they just collect whatever they happen to encounter, you're just going to get the same stuff that you've seen before. And so if you know that you're learning, the question is, what should robots do to learn better? That means automating this process so that robots can do it on their own. It's really a control challenge. And so I think of this as control for learning. Learning for control is taking the enormous amount of tools that are now at our disposal to improve the way robots operate in the world, but this is using control theory to make them better learners in their environments. And so as much as possible, I want to have robots that work in unknown environments with unknown sensors, with no pre-existing data, no pre-training, no supervision, and see what happens. So this talk is about why I think that's possible, but it's not a prescription of how to do it. So to give you a mental picture of what I mean, this is a simulation. I'll show you a hardware version of this in a second. We think a lot about rubber ducks in my group, by the way. And what you're seeing is a robot that has an uninitialized neural network, and as it collects data, it's regressing the neural network in real time. And it's building a model, and how it looks, it doesn't even know that there's a rubber duck. It doesn't know what sensor it has. This is just done because vision is legible for an audience. And some things that are worth just noting in that video is that the rubber duck spends a lot of time in frame, which is interesting because the robot doesn't know that there's a rubber duck there. That's entirely driven by the entropy of the neural network. And it also spends a lot of time at the edge of the frame because that's when it's hardest to produce generative predictions. It's when the rubber duck is slightly occluded. And so the question is, the optimization and control question is, how do we automate this process of the robot responding to the evolving neural network? And so here is this mess of a block diagram that the important part here is that you're collecting data, you're training a neural network, you're making predictions both about the maximum likelihood prediction that you expect, but you're also making uncertainty predictions. And then you're closing the loop on that uncertainty as a function of space in the domain. And then the question for this talk is, what should the controller be that responds to that uncertainty in the neural network? So the whole purpose of this closed-loop system is to regulate the evolution of the neural network as it evolves. There's no training set and testing set. The robot is constantly training and testing at every moment in time. And so the way that we do this is by exploiting something called ergodicity. The short version is that ergodicity relates time-averaged behavior of a trajectory to the spatial statistics of a distribution. The trajectory comes from the physics, the spatial statistics come from something like an expected information density in the environment. You can think of ergodicity as being a generalization of Kullback-Leibler divergence, but that is well posed for trajectories instead of distributions. And ergodicity what it does is it gives you coverage, so it gives you data collect from the places in the environment that are most important to you, but it does it while simultaneously decorrelating the data. And if you think about your sort of foundations of statistical learning, decorrelated data is the axiomatic starting point for everything that you do in regression. Because if you have really correlated data, you're going to end up primarily learning the correlations rather than learning the distribution that you're trying to extract. And so ergodicity as a control synthesis method, it decorrelates the data while allowing you to prioritize some data over other data. This, unsurprisingly, allows you to do things like optimize packed learning properties, specifically the IID requirement that shows up everywhere in packed learning. Okay, so imagine now that I've told you I'm going to give you a robot. The robot gets to know how to move. That's not actually an essential part of this, but the robot gets to know how to move. It doesn't get to know anything about its sensors, and it doesn't get to know anything about the environment. But it has to build a representation at runtime, and it has to do it reliably. Some examples, so camera data, I've put these in the order of pixels that you would see if you were looking, but from the robot's perspective, that's just a big, nasty vector of signals. It doesn't have any of that sort of proximal information about pixels having relationships to each other. Touch data, so it's sort of a camera that's responding to a membrane. Ultrasound data, I think, is particularly nice because ultrasound is a very, very wild environment to build perception models in. And the goal should be that a robot, you just strap your sensor to the robot and it learns a model based on whatever sensor you happen to give it. And this is what that looks like. So it's fine to have multiple objects. The robot doesn't know that there are objects to begin with, so just any place in the domain that is feature-rich that the neural network can be responsive to, it's going to collect data that's independent about those different features. It can actually, turns out the entropy predictions are quite good at segmenting the environment into different distinct, what you might think of as objects. That's what the lower left panel is showing. And in this case, it learns 4 distinct objects. It learns about what we would call the star and what we would call the rubber duck. It also learns that blank regions have their own descriptions and that they're highly correlated to each other. But now you can run the exact same approach and with an ultrasound. And so this is, we've embedded a rubber duck in Jello, so we can't visually see it. But the robot moves, and as it's moving the ultrasound through the Jello, it detects the patterns associated with the rubber duck, and it builds a model of the rubber duck. It's not easy to actually see the rubber duck in the images, but the neural network is quite robust at detecting those signatures. And then this one is particularly fun to look at. So the upper left image, when the robot is touching the rubber duck, it is getting very, very irregular signatures in that touchpad. And so the robot learns very quickly. So it doesn't know where the rubber duck is. It has to discover where there's interesting information. And then once it finds it, it just sort of pokes at it a lot until it builds up a representation of what that object feels like. The key thing here is that this robot is genuinely locked in a room. It's not able, it doesn't start with anything. It starts with an uninitialized neural network. And these representations take a few minutes to regress. This is not a long process. But the thing that is challenging about it is that you have to synchronize your neural network regression with the motor control of the robot. It turns out that that's quite a bit of effort. There's nothing offline allowed in this setting. Okay, so challenge problems for the community. We hear a lot about LLMs. I'm interested in all of these things. I am now less of a cranky old guy, but I would claim that a really, really interesting problem is imagining a robot completely uninitialized that wakes up in your home, and a year later it's supposed to be able to meaningfully speak portions of your language. It can only do this through interaction with you and observation of you. It can't just passively watch whatever happens to be going on. It's gonna have to generate its own labels and then correlate those labels to things that are happening when people speak. I'm happy to give the robot phonemes if that makes your job any easier, by the way. I think autonomy that builds environmental models in large, unstructured environments for which we have little data is an important problem. So like over days and weeks and months without any supervision, potentially without any communication, space and water and other harsh environments where we typically don't have a lot of data, maintaining custody of novel agents. I think a really interesting problem is if you have a robot deployed in underwater settings and you're trying to detect invasive species, a really interesting way of framing that problem is that there's just something that's not supposed to be there. Instead of saying, this is the invasive species that I'm going to try to detect, I'm going to say, there's a thing. And now I'm going to go and collect on that thing. And I'm going to track that thing. And because, the thing might be something else invasive that you weren't anticipating. I think untethered experiments, physical experiments, not simulated experiments, by the way, are really worth doing. So you're going to hear about social navigation in a second. This is an untethered robot in my group that it has a Jetson that is powered by the robot's own battery. It has to regress models of all the agents in the environment as it moves around in the environment. This is a very, very hard problem, and people are extremely stressful to learning algorithms in terms of interaction. Also, severe mechanical degradation. I'm not going to show this because you probably find it upsetting, but we light robots on fire and then make them relearn how to do things. We chop up their actuators and make them relearn how to do things. I think this is the right way to go. And these are experiments that are different than what we're typically able to do. So, along the lines of what we've heard before, I would say more data is not the answer. I think figuring out how to take the right data is the answer, and that it can do things like if you know you're taking the right data, that's also going to improve stuff like certification, which we just heard about. So, this is just recapping everything that I just said, but I think with that, we're good for questions.
Great. Thank you very much, Todd. So I stand corrected. So he does lock up robots in a room and tortures and mutilates them. We have questions. And while Todd takes question, Angela, maybe you can set up. Okay.
Hi, thank you for the talk. I was at a panel yesterday, and they were all talking about how human priors should be more included in robotics in order to kind of get to a final state where human-robot interaction is safe. It looks like all of this work is kind of like a completely randomly initialized network. So I guess what are your opinions on that?
Okay, so I also am a believer that we are going to have to figure out what the role of priors. I think one of the risks of assuming that priors should play a role is that it also assumes that we have, in some sense, the right priors. Many priors, the robot is going to spend as much time unlearning those priors as it does exploiting them. And so sort of the right way to include what we do want the robot to infer something from while also excluding the things that are not relevant. I would say the ultrasound experiments are a good example of that we have a mental model of how ultrasound should work that is not particularly connected to the way it really physically works. And the robot is actually able to generate perception models much more quickly if you just let it do it from an uninitialized state. So it's more that the prior question is just much more complicated. On my last slide, I comment, we have to figure out how to include priors. I'm not sure that there's a good model for that yet.